Welcome you all in my next lecture. So in this lecture I will talk about functions from m-dimensional Euclidean space to n-dimensional Euclidean space. Then I will give various definition of functions, that means real valued functions from n-dimensional Euclidean space. Then we have Rn valued functions from set of real numbers. Then we have finally Rm valued functions from Rn dimensional Euclidean space, and then I will introduce the notions of limit and continuity, and then see what sort of definitions we will have in the context of n-dimensional Euclidean space. Okay, so let's start with the definition of functions from n-dimensional Euclidean space to m-dimensional Euclidean space. So let f be a function. So let capital F, I am denoting capital F. So let capital F be a function from the set S, which is subset of n-dimensional Euclidean space to m-dimensional Euclidean space, where n is greater or equal to 1 and m is greater or equal to 1. Okay, let's see. So now if both n and m are equal to 1, so that means I have a function f from where? R to R. So that means I have a real valued functions of real variable. Okay, what will happen the second? Second, I am saying that, okay, consider n is equal to 1, but where m is greater than 1. So that means I have a function, so I have a function capital F, which is from n is equal to 1. So then it is a subset of R, and then it is taking the value in Rm, that means m-dimensional Euclidean space. So that I am saying it is called a vector valued functions of real variable, or more briefly a vector functions. Now if I do the reverse part, that means consider n is strictly greater than 1 and m is 1. So in that case, what is my functions? My functions capital F, which is from Rn to R. So that means I have a real valued functions, but my domain of the function is n-dimensional Euclidean space. So that's why I am saying that the function is called the real valued functions of vector variable, because my domain of the function is n-dimensional Euclidean space, or more briefly it is called a scalar field. Finally, if I have both n is greater than 1 and m is greater than 1, then what will happen? When both n and m are greater than 1, it is called a vector valued functions of a vector variable, or simply a vector field. Okay, let's see some examples. Okay, so consider this function first, real function. So that means f of x is equal to x square plus sin x. Of course, it is a functions from R to R. So therefore, it is a real valued functions of real variable. Next example is the vector functions. Vector function means what? We have noticed that vector function is a map from set of real numbers to n-dimensional Euclidean space. So now here what is the example? I am considering a functions, or I am saying that motion of a particle moving in the space, that means it is a map from R subset of real line to 3-dimensional Euclidean space. So that is my motion of a particle moving in a space. So how I define it? It is R of t. What is the component? This is t, 2t and e to the power minus t for t greater than 0. So this is kind of vector function. I mean, it is a functions from 1-dimensional Euclidean space to n-dimensional Euclidean space. Next is that scalar field. That means I have a functions from n-dimensional Euclidean space to real valued. So now this is the example. So this is called scalar field. So the temperature at any point in a cube. So that means I am denoting as this function t, which is subset a subset of R3 to R, defined by t of x comma y comma z, which is x square minus 2y plus 5z cube. And what is my cube? This is mod x less than 1, strictly less than 1, mod of y strictly less than 1, and mod of z strictly less than 1. So this is scalar field. And finally we have the vector field. That means I have a functions from n-dimensional Euclidean space to m-dimensional Euclidean space. So that is, I am saying that the temperature and pressure at any point in 3-dimensional object is like examples of this kind of functions. So that means I have a functions f from R3 to R2. What is my definition? I am saying that f of x, y, z, which is nothing but x square plus 3y comma y plus z, where mod x is strictly less than 5, while lying between 0 to 1, and mod z is strictly less than 1. So sometimes this is called the vector potential functions. V of x, y is nothing but, this is the way I have defined, x square plus 2 comma e to the x plus 3y, where my mod x is less or equal to 1 and mod y is less. These are the kind of few examples of kind of various kind of functions, like from R to R, Rm to R, R to Rm, Rm to Rn. So these are the examples. Okay, so now this is very important. So that means what I am trying to say is that if I have a functions capital A from say n-dimensional Euclidean space to m-dimensional Euclidean space, then I can have the representation of this function as a coordinate or component function. Just like we have noticed, if I have a sequence capital Xk in Rn, then corresponding to that capital sequence Xk, we have n many coordinate sequences of real numbers. Similar sort of things I can have in the context of several variable function. Let's see how things going on. Okay, so let f be a functions from S subset of Rn to Rm, where n greater equal to 1 and m greater equal to 1. Then what I am doing is that, so let x capital X, which is a point in S, then capital F of x, this is the value of capital F at the point capital X, which is small x1, small x2 up to small xn, that can be written as this kind of object. That means capital F of x, which is nothing but f1 of x, f2 of x, fm of x. So what is f1 of x? So now I have written where f of I, small f suffix I, is a real valued functions, but in domain is Rn. So that means I have a functions. That means the function fi, it's a map from S subset of Rn to R. So that means given a functions capital F from Rn to Rm, I can represent that function capital F into m many components, f1, f2, fm, where each fi is a real valued functions from the set S subset of Rn. And how I define the function small fi? So I have written, so small fi at x is nothing but inner product between capital Fx and ei. What is my ei here? So here ei is a vector in Rm such that ei where ith position is 1, rest of them are 0. So that means it is 0, 0, 0, 1, 0, where this 1 appears at the ith positions, and this is an element in Rm. Because I am taking the inner product of capital Fx. Now look, what is capital F? Capital F, x, capital X is a point in Rn. So capital F acting on x is a point in Rm. I am taking the inner product between two vectors of Rm. Capital F of x is a point in Rm. Ei is an m tuple where ith coordinate is 1. So therefore, if I take the inner product, it will exactly the fi of x. So that's how I define. So therefore, given capital F from Rn to Rm, I am defining a small fi, which is the real valued functions of n dimensional, or is a real valued functions from the set S. S is subset of Rn in this way. So I have written, and it is called the what is called component functions or coordinate functions of f. So that means what I observe, this is very important observations. That means if I have a functions capital F from a set A subset of Rn to Rm, then that capital F I can write as m components like f1, f2, fn, where each fi is a functions from the set S, which is subset of Rn to R, real valued. If m is equal to 1, then you can easily observe that this component function capital F is boils down to the functions f itself, because there is m is 1, that means already real valued we will have. Okay. So why this representation is important? Because later on you will see, like earlier we have seen, if I have a sequence capital Xk, then we will have corresponding n many coordinate sequences, and we have seen that convergence of the sequence capital Xk is equivalent, or if and only if the convergence of the component sequence or boundedness of the component sequence implies the boundedness of the sequence capital Xk. So these are the properties we have already observed in the context of sequences. Now similar sort of things whether we can achieve in the context of, say, when I will talk about the concept of limit. So existence of limit for capital F, whether this is equivalent to the fact that existence of the limit of the component function, or say once I have the notions of say continuity of capital F, say Rn to Rm, whether it is equivalent to the concept of continuity of the component function. Equivalent means what I am saying is that suppose capital F is continuous, is it implies that all the component functions, that means real valued functions of this n many variables, so whether these functions are continuous, or whether the component function continuity implies the continuity of the kind of Rm valued functions of Rn variable. So these are the questions like, or maybe what sort of interplay between the component functions and the main functions, how it behaves. So that we will see later on, and you will see that similar sort of things like in the case of sequences happen, similar sort of things also true in the context of functions as well, at least if I talk about the concept of limit and continuity. Okay, so before that let us see some examples. Okay, so let capital F is a functions from say 4-dimensional Euclidean space to 5-dimensional Euclidean space. So that means capital F, you will see that I will have kind of 5 components. So, value of capital F at x1, x2, x3, x4. So, this is the component functions. So, x1 plus x2, x1 square, x3 exponential of x1, 5x2, x4. So, by looking at the definition of the function capital F, you can easily recognize what are the component functions. So, that means component function fi should be a map from R4 to real valued functions. And what about the first component functions? It is a map from R4 to R, and how it's defined, f1 of x1, x2, x3, x4, which is nothing but this is the one. Then similarly, what about the second function? This is x1 square. What about the third component function? x3 times exponential of x1. What is the fourth component function? It is 5 times x2. And what is the component function 5, which is x4. So, just by looking at the definition of functions capital F, you can easily recognize what are the component functions. So, therefore, I can write capital F, which is f1x, f2x, f3x, f4x, f5x for x is in R4. So, I have written that those functions, that the functions fi are called the component function, or simply I will say that it is a components of f. So, this is by looking at, also you can use the definition that this is just what is my fi. So, fi of x, which is nothing but capital F of x inner product with ai. What is ai? Ei, now ei is a vector, ai is a tuple in R5. So, that means I have 0, 0. Suppose this is my E2. If I say that, okay, so let it be F2 of x, which is nothing but Fx, comma E2. Okay, so what is my E2 here? E2 is nothing but 0 at the one place, 1 appears at the second place, then I have 0, 0, 0. So that's how it is. Similarly, you can have F1, small f1, small f3, small f4, small f5. You can easily do that, and it kind of boils down to the fact that F2x is nothing but this function. Okay, so now I want to talk about the concept of limit for several variable functions. Before that, let me just recall the concept of limit in the context of real valued functions of real variable. Okay, so that's just a recall. So, limits of real functions. So, if I have a function small f from a subset of R to R, suppose you have a real function, then so if I start with a limit point A is a limit point of S, then I will say that a point B is said to be a limit of f at A, which I denote it like that. That means limit x approaches to A, f of x is equal to B. If given epsilon, there exists a delta such that the following is true. So, given epsilon, there exists a delta such that if I take any x in S, if the distance between x minus a is less than delta, it should implies that distance between fx and b is less than epsilon. Note that if I start with epsilon, the delta depends on epsilon and the point a itself. So, therefore, given epsilon, I have to, there should exist a delta which depends on epsilon and a, such that if I take x from the deleted neighborhood of A. That means what? That means you see this is 0 is strictly less than, that means A is not included in this neighborhood. So, that means this is a neighborhood of A around delta, but the point A is not there. So, that it should implies whenever x is coming from this set, the difference between fx minus b less than epsilon. Now, it is very important to note that while talking about the limit of a function at some point, that point, suppose I am talking here the limit of the functions at the point A. So, A need not be a point in the domain. In other words, I do not need A should be a point in the domain, so that f of A is defined. Even if my point A is not in the domain, but it is a limit point, then also I can talk about the limit of f at that point. That is very important. That is why I am having that x belongs to x, but x mod of x minus is less than delta, but it is strictly positive. That means you do not need that A should be a part of the domain, because I do not need the value of the function at A. It is not necessary. It could be in the domain, that does not matter. But I can talk about the concept of limit a point A, that point need not be in the domain of the function. It could be a limit point. So, that is why this is true. So, therefore, in this case I will write if these things happen. So, that means given a function A, start with a point A which is a limit point, I will say that that point limit of the function f exists and the value is b if given epsilon there exists a delta which depends on my point A and epsilon, such that whenever I am considering x from the deleted neighborhood of A, that means there exists a delta which is depends on epsilon and A, and if I take the point from this neighborhood except the point A, then the fx minus b, that distance should be less than epsilon. That I think we are familiar with in the context of real valued functions of real variable. If these things happen, then I will say that limit is exist. In other words, one can say that fx approaches to b as x approaches to a, or fx has the limit b as x tends to a. So that means if x is, so suppose this is my point a, suppose this is one dimension, suppose this is my point a, I am saying that if x approaches to a, then my limit f of x, which is the value of the function at x, approaches to b. That's what's the meaning. But there is a catch actually. What is the catch? So now my point is that, so this is the concept of limit we are familiar with for real valued functions of real variable. Now look, now if x approaches to means what? In real line, I have only two directions. So that means I can approaches to a either from the left hand side or from the right hand side. Let's see what sort of definitions I will give the concept of limit in the context of several variable functions. Okay, let's see. Okay, so now this is the corresponding notion of existence of limit for several variable functions. What is that? Okay, start with the functions capital F. So start with the functions capital F from the set S subset of Rn to Rm. So this is my functions. I am starting with a point capital A, which is small a1, small a2 up to small an, see, which is a limit point of S. Okay, so now I am saying that a point B, capital B, which is b1, b2, bm, is said to be a limit of capital F at a if for whatever epsilon I can take, for every epsilon there exists a delta, and again that delta depends on epsilon and at the point A, such that if capital X belongs to S, such that norm of x minus a, which is less than delta, but remember norm of x minus a is strictly greater than 0. That means x cannot contain the point capital A. That is very important, which should implies that norm of fx minus b, which is less than epsilon. If these things happen, then I will say that limit capital X approaches to a, capital F of x is equal to b. So what is the difference between the definitions of real valued case and several variable case? There is nothing. So I am just replacing the modulus part by a norm in the context of several variable. So same definition. So I am starting with the functions capital F, okay, from set S subset of Rn to Rm. I am taking a limit point capital A, and then I want to talk about the existence of limit of capital F at the point A. So if these things happen, that means given epsilon, if I find a delta which depends on epsilon on the point A, such that whenever I am taking the point from the deleted neighborhood of A with radius delta, then the difference, the distance between capital Fx and B should be less than epsilon. If these things happen, then I will say that my limit exists, and which is nothing but this is. In other words, I say that capital Fx approaches to B as x approaches to A, or Fx has the limit as x tends to A. So that means similar sort of definitions, whatever available in R, the similar sort of things also true in Rn or Rn to Rm functions, but just I am replacing mod by norm. So this is the moral. What is my moral? Concept of the limit of functions in multivariable calculus is essentially same as that of concept of the limit of functions in single variable calculus. Now the concept, so this is important. So it says that concept of limit is same, but it has a deeper insight. What does it mean? Mean is that in multivariable calculus, the definition of limit capital F has the following deeper insight that was not there in the real variable case. What are those? So capital X approaches to A. What does it mean? It means that x can approaches to A along any path or curve. That is very important. For example, in real line, as I told you earlier, if I have a point A, so I can approaches only in two directions, either in the left or in the right. But instead of R, if I am in say Rn, that means if I am in R2 or R3. So suppose, let me take an example. So suppose this is my R2 and take a point A, capital A, which is nothing but A1, A2. Now, how many direction I can approaches to A? Infinitely many. So I can approaches to A in this direction, I can approaches to A in this direction, I can approaches to A, I will go in this way and then go back this, and then I can come in this direction, I can come in this. So there are infinitely many ways I can approaches to capital A, at least in R2. This is the picture I have drawn, this picture in R2. Similarly in R3, Rn, so if I have a point, there are infinitely many ways I can approaches to A. So now the point is that if all the direction, whatever direction I can choose, if I approaches to A, the value of the function f of x, capital F of x should approaches to the same point. So that's what I have written. So capital Fx is approaching always the same point or value B, irrespective of the path on which x approaches to A. So that is very, very strong conditions. That means in the domain set I have a capital A, and whatever directions I can approaches to A, whatever path I can take, the value of fx approaches to the same value. That is very important. In such a case only, so this is very, in such a case only, if these things happen, in such a case only, we are saying that the limit of capital at x exists as x approaches to A. Okay? So that means another way, so that is along each path on which x approaches to A, the functions capital F of x is always approaching to the same value. If this is the case, then I will say that limit of the functions capital F as x approaches to A exists, and which is exactly equal to the value b. So that is very important. In our case, we have only two directions, but when I will go to the several variable case, then you have infinitely many directions. So therefore, I need a strong definitions. So once I have the definition, the earlier one I have given in terms of norm, it will implies the definition. It says that if I approach whatever directions to A, the value of capital Fx approaches to the same value b. If these things happen, then I will say that the limit of the functions as x approaches to A exists, and its value is exactly equal to capital B. Let us see some examples. Okay. So I have a functions small f which is at xy. So this is a functions from R2 to R. So these are functions. So I want to calculate the limit xy approaches to 0, 0, that means origin, the value of the limit, what will happen. So there are three steps. First step, somehow you have to guess what sort of limit you can expect, and then you have to use the principal definition, that means epsilon delta definitions, and show that my definition is true, and therefore you can conclude that your limit is like that. So this is a step one. What is my step one? Deciding to show that limit exists and guessing that what should be the possible limit value. So what is the limiting value? So in this case, we can expect that limit will exist. So that's my kind of, I'm guessing the limit will exist, and limiting value say b is equal to 0. That's my initial guess, but I have to prove it, right, in terms of epsilon delta definitions. So what I will do next step, so then I have to estimate. So if I guess that b is equal to 0, somehow I have to see that I have to find deleted neighborhood. So that means suppose this is my R2, suppose this is my origin. So I want a neighborhood. So given epsilon, so that means given an epsilon, so if I have a epsilon positive, I have to find a delta, a neighborhood around the point 0, 0, such that whenever the point is coming from here except the point 0, 0, my distance between f of xy minus b, it should be, I should make it less than epsilon. So this is the procedure. So I have to estimate in the puncture neighborhood, that means the deleted neighborhood, you have a neighborhood of around the origin except the point origin. So let us estimate. So given f of xy is given, the definition is given. So norm of f of xy minus 0. So that means I have what? I have simply norm of or modulus of. So this is, I should say modulus, because it is taking the value in real. So modulus of x sine 1 by y plus y sine 1 by x, and this is 0, so not an issue. So this is dominated by, because sine and sine functions dominated by 1, so therefore this is less or equal to mod x plus mod y. That's what I have written. So therefore this is always true for all xy in a deleted neighborhood of 0, 0. And what is the step 4? So given epsilon, I have to find a delta. So that's the kind of explicit kind of construction of delta. So start with epsilon positive, choose delta is equal to epsilon by 2, then what will happen if xy lies in the deleted neighborhood, that means if norm of xy minus 0, 0, which is nothing but square root of x square plus y square, if it is less than delta, which is exactly equal to epsilon by 2, I have chosen delta like that, then the norm of fx minus fy, which is already, I have this estimate mod x plus mod y, and this is certainly less or equal to 2 times square root of x square plus y square. Why? Because modulus of x is always less or equal to square root of x square plus y square, and similarly modulus of y, which is always less than x square plus y square. So therefore this will implies 2 times square root of x square plus y square, but I already chosen that xy distance from 0, 0, which is less than this. So therefore this is the adjustment, 2 times delta is epsilon by 2, and this is epsilon. So therefore given epsilon, I can have a delta which is nothing but epsilon by 2, such that if distance between xy and 0, 0, which is less than epsilon or less than delta, then my corresponding value of f of xy minus 0, which is less than epsilon, and that is nothing but the definition. Therefore I can say that yes, limit exists, and the limit of f as xy approaches to 0, 0, it is exactly equal to 0. Okay, so I have not written. So this is, that means I will say that. So this is, the value should be 0. Okay. So that means what? So that means I have proved this limit, that limit exists. This automatically implies that whatever direction I will approach is to 0, 0, the value of f at small f at xy always approaches to 0. So now to show that limit does not exist, so this is the kind of argument we can use. Suppose I want to show that the existence or limit of f at some point x approaches to a does not exist. In that case, what I will do, so take the point wherever I want to check whether the limit exists or not. What I will do, I will take two different paths which approaches to the point A, but I will show that the value of the functions approaches to different limits. If these things happen, then I will say that my limit of the functions at that point does not exist. So that's what I have written. How to show limit does not exist? So how to show limit does not exist? To prove that one can use that, take two different paths, both approaches to A, and so that the corresponding value of the functions approaches to different limit. So then I am done. That's what I have written. So if we want to show that limit x approaches to a fx does not exist, then it is enough to show one of the following. What are the things? Number one, capital F of x is approaching to two different values, say b1, b2, while x approaches a along two different paths. So that means, again, I am supposing R2, suppose I want to check the existence of limit at that point. What I will do, take two paths. Suppose this is one path, and suppose this is another path. So in this path I am approaching to a, in this path I am approaching to a, but the corresponding value of the function approaches to say b1 and b2. If these things happen, then I will say that limit does not exist. Because if limit exists, then whatever directions I will choose that I will approaches to a, the value of the functions, if the limit exists, the value of the function approaches to the limit of this function. So that is important, that follows from the definition. So therefore, if I choose two different paths, both approaches to a, but the corresponding values approaches to different limit, that means limit does not exist. Second one, there exists a path on which the functions fx is not approaching any point as x approaches to. So that means if x approaches to a, if the value of the function is not approaching to any point, then also it means that limit does not exist. And what about the third one? If there exists a path on which the functions, that means norm of fx approaching to plus infinity, in other words, norm of fx blows up if x approaches to a, then I will say that in this case also limit does not exist. Okay, so let's see some examples, then it will be more clear. Okay, so suppose I have a functions small f, again it is a functions from where? It is a functions from R2 to R. Okay, now I want to examine whether this limit exists or not. That means whether limit of the functions at the point 0, 0, whether this exists or not. So, but one point you just notice that this function is defined at a non-zero point, but still I can talk about the limit at the point 0, 0. As I said earlier, to talk about the limit of a function at some point, that point need not be in the domain. It could be a limit point, but 0, 0 here is a limit point of the domain set. Okay, so let's see how I can proceed. So step one is that deciding to show that whether limit does not exist. That's my guess. So in this case, what I will do just now I said, so in this case we expect that limit will not exist. That's my guess. We shall find two paths. I will find two different paths where f approaches to two different limits. So that means this is my origin. This is my origin. I will find two different paths, both approaches to 0, but the corresponding value approaches to two different limits. So this is step 2, path 1. So what I am doing? So take y is equal to x, x is non-zero, and so that means I have this my origin. Actually, I am approaching to 0 in this direction. So y is equal to, so this is y is equal to x. So if I approaches in this direction, let's see what the value of the function approaches. So this is my gamma 1, so that means this is my path, y is equal to x, x is non-zero, and x approaches to 0. So in that case, what will happen? So in that case, certainly if x approaches to 0, that means xy approaches to 0, 0. Along, I think this should be typo, this is gamma 1. Okay. So then what will happen? Now y is equal to x, so therefore small f of xy, what is the value? Put y is equal to xy, this should be x square by x square plus x square, that means it should be half, so that means it approaches to half. So that means if I approaches in these directions, the value of f at x approaches to in this direction to the value 1 by half. Let's take another path, path 2. So if I take path 2, y is equal to 2x, again, so that means I am approaching to 0, 0 in this direction. This is y is equal to 2x. Okay, so I am bad at picture, but again, you just believe that this is the y is equal to 2x1 and I am approaching to origin in this direction. Then what will happen? Put the value y is equal to 2x in this function, then what will happen? I have the value of f at xy is 2x square by x square plus 4x square, which is 2 by 5, and this is a constant function, so therefore this approaches to 2 by 5. So that means what is going on here? So that means if I choose the path gamma 1, which is nothing but the line y is equal to x, if I come to the origin in that directions, then the value of f approaches to half. If I take y is equal to 2x, and if I come to origin in that directions, my value is to 2 by pi. So now I have two different paths, both approaches to origin, but the value of the function approaches to two different points. Therefore, I immediately say that limit does not exist. So therefore, f approaches two different values as xy approaches to 0 along two different paths. So therefore, limit does not exist. Okay, so this is algebra of limits. So if I like in the real valued functions of real variable, we know that means sum of two. If the limit exists of two functions, then the sum function limit exists. Scalar multiple, product, similar kind of things also true here. So if I have two functions, capital F from Rn to Rm, capital G from Rn to Rm, and suppose x naught is the limit point of S. Suppose this limit x approaches to x naught capital Fx, limit x approaches to x naught capital Gx. If this is exists, then the sum will distribute like that. So limit x approaches to x naught capital Fx plus capital Gx, the sum will distribute. Scalar multiple, if I hit it, lambda will come out. If I take the inner product, I can push the limit inside the inner product. So that means limit x approaches to x naught, inner product fx gx, which is same as inner product of individual limit. So that means I can push the limit inside the inner product. Similarly, if I take the limit x approaches to x naught of norm of fx, that means positive valued functions, then I can push the limit inside the norm. In fact, these two properties actually true. Later on you will see, since norm and inner product function, they are continuous functions. So therefore, I can interchange limit and the inner product and norm. That you will see when I will talk about the continuous functions, notion of continuous function in Rn. In particular, if I take m is equal to 1, that means if I have a real valued functions, then I can have the notions of difference. So therefore, I can talk about, suppose if the limit is non-zero, then the limit of the quotients, limit x approaches to x naught fx by gx, which is similarly same as limit x approaches to x naught fx divided by limit x approaches to x naught gx. Because I am taking m is equal to 1, so that means I am real valued, so therefore division makes sense and I can do that. Okay, so as I said, so is there anything, so like I have defined, given a functions capital F, there are kind of notions of component functions. Now in the sequences, many things or many kind of conclusions I talked about of the original sequence by giving some conclusion on the component sequence. Similar things is true in the context of existence of limits. What it says that, so let capital F be a functions from the set S subset of Rn to Rm, which is a functions. Then I know capital F has a representations, so I can write capital F as m many components, that means small f1, small f2, small fn, where small fi are the component functions of capital F. Let x naught be a limit point of S, and let capital L, which is small n1, small l2, small lm, is a point in Rm. Then this is the following is true. What is that? The limit capital X approaches to x naught capital F of x is equal to L, if this is if and only if all the component functions limit exist and the limit of small fi is nothing but small li. So that is very important. So that means if I have a function capital F, and if it of course corresponding to that capital F functions, I have m many component functions, existence of the limit of the original functions implies the existence of the limit of the component functions. Existence of the limit of the component function implies the existence of the limit of the original functions. Using that, you can have plenty of examples. If I say that, okay, calculate the limit of these functions, you just look at the component functions, get the limit and conclude that, okay, this is the limit of the original functions. Okay, so let's see some example. So that is important. Okay, so let capital F, it's a map from R2 to R3, is a function which is defined like that. Capital F of xy, which is sin x by x, x square by x square plus y square, comma 5y. So I want to find the existence of limit of these functions, okay, around as xy approaches to 0, 0. So what is my first step? So since the definition of capital F is given, so you just immediately identify what are the component functions. So first component functions, f1 is a map from R2 to R, which is that f1 of x comma y, which is sin x by x. That is the first one. So now what is f2? Again, f2 is a map from R2 to R. So what is f2? So f2 is a xy is x square y divided by x square plus y square. And what is f3? Again, f3 is a map from R2 to R. And what is f3? f3 of xy, which is nothing but 5y. So now just to apply the earlier theorem, if I see the existence of the limit of the component functions, I can conclude the existence of the limit of the original function. Let's see. Now, if limit xy approaches to 0 f1 of xy, which is nothing but limit xy approaches to 0 sin x by x, and all we know that this limit is always 1 from the single variable calculus. Second component function, let's see, limit xy approaches to 0 f2, which is same as limit xy approaches to 0 this one, and this limit is 0. Why? Because what you do, this is x square y divided by x square plus y square, okay, minus 0, take the modulus. Now, this is always dominated by mod y divided by mod y, that is it. Because what? Because x square plus y square is always greater than x square. So, therefore, 1 by x square plus y square, which is always less than 1 by x square, sorry. So, yeah, so that means 1 by x square plus y square, which is always less than 1 by x square, right. So, this is always true. So, therefore, this quantity I can always make less than modulus of y. Now, if xy approaches to 0, so therefore, right hand side approaches to 0, and therefore, the left hand side goes to 0. So, that is why this limit exists, and limit is always equal to 0. What about the third component functions? So, limit xy approaches to 0 f3, which is nothing but limit xy approaches to 0 phi y, and this is by trivial that this is goes to 0. So, therefore, I have proved that all the limit of the component function exist. So, what are the value? 1 0 0. So, therefore, the limit of the original function exists, and the value is 1 0 0. So, this is the existence. Okay. So, let us see one example what my function is not limit does not exist. Okay. This is another example. So, take capital F from R2 to R3. This is my definition. Okay, like sin x by x, y by x square plus y square, comma 5. So, then by looking at the definition of capital F, you can easily identify what are the component functions. The first component function f1 of xy, which is nothing but sin x by x. Second one f2 of xy, which is nothing but xy divided by x square plus y square, and third one f3 of xy, which is exactly equal to 5. Now, first one limit exists, not an issue, I just explained. Look at the second one. So, let xy approaches to 0 f2. So, therefore, limit xy approaches to 0 xy by x square plus y square, and that limit does not exist. Why? Because if I approaches to, so this is in R2, so that means if I take the origin, because f2 is a function from where to where, it is a function from R2 to R, and I want to investigate the existence of limit at the point origin. So, now look, so if I approaches to the origin, say y is equal to mx, this path, then what will happen with that one? If I put y is equal to mx, then this value should be x square divided by y is equal to mx, so that means mx square by y is equal to x square plus m square x square. So, that means this is same as m divided by 1 plus m square. So, that means it differs from different values of m. So, that means if I approaches to 0, if y is equal to say m1x, the value will be the value of f2xy will be, or f2xy approaches, what is the approaching value of f2xy? It should be m1 by 1 plus m1 square. If I approaches to y is equal to m2x, y is equal to m2x, where is the small f2 approaches? The value will approaches m2 by 1 plus m2 square. Now, if m1, m2 are different, the corresponding values are different, so therefore, limit does not exist. What will happen for the third one is a constant function, limit always exists, fine. So, now I have investigated, given that function capital F, I have the component function. First component function limit exists, third component function limit exists. What about the second one? Second one limit does not exist. So, therefore, if I apply the earlier theorem, that means limit of the original function exists if and only if limit of the component function exists. That fails here. That means in the second component functions limit does not exist, and therefore, the limit of the original function does not exist. So, I think that is all for this lecture. Next lecture I will talk about more on examples of the limit existence of limit, and of course, I will talk about the concept of continuity. Okay, I think I should stop here. Thank you.